Okay. Well, day morning session. Our first speaker is Nakano. Talk about realizing triangular quasi-hereditary. One covers for Hecke algebras.
Yeah, so I'd like to first thank the organization and for the invitation to come here. I mean, it's really great to be able to come here. It's my first time in Eastern Europe. So what I'm going to do is I'm going to speak on joint work with Chengdu Lai and Zijing Xiang. So this talk will be somewhat historical. So I'm going to start out sort of from the beginning in terms of how this sort of theory got started. So what I'd like to do is I'd like to first talk about the subject of spectral aliases. Now I'm hoping that this theorem that I put up will be understandable to everyone. Okay, so this is a theorem that I proved with Hecke about 20 years ago. And it says the following. So let K be a field of characteristic P bigger than or equal to 5. Okay. So then that filtration will implicitly for the spectrum models of the group algebra are volatile. Okay, so just like with the composition factor multiplicities, they're all defined by the Jordan-Porter theorem. These modules, the spectrum modules, are not necessarily irreducible. They're reducible in characteristic 0, but they're not necessarily reducible in characteristic P. Under this condition, for P bigger than or equal to 5, they're still indecomposable. And you can ask if you take a filtration where the subsections are strict modules. You take another filtration where the subsections are strict modules. Do they actually coincide with the characteristic? So i.e., I take number of times the strict module appears and the filtration for M is this formula. Okay. Now, this is a conference on Hecke algebra. It's a conference on quantum algebras. So this has an analog for quantum groups. So let me first mention this theorem. All right. This is not true for P equals 2 and 3. But there are actually counterexamples of when P equals 2 and 3. And if you want to see the counterexample, see Mark's example. On 12. Okay, so now this has an analog for the Hecke algebra of type A. So the statement holds for H, which is the Hecke algebra of type A. So as long as the order of the root of unity is bigger than root over 4. And so we'll see so it has an analog in the quantum situation too. Okay, any questions on this theory? Okay, so now what I want to do is I want to explain why this theorem is true. Why is it true for P bigger than or equal to 5, and why is it not true for P equals 2 and 3? So in order to do that, I have to talk about Schur volume drama. Wow. All right, so this is actually mentioned in Monica's talk. So I'm going to talk about the tensor space and looking at the actions on tensor space. So let me look at what's called the Schur algebra. So this is S. So this is S, Q, and D. And so this is going to be the endomorphism algebra of the Hecke algebra type A, and it acts on the tensor space. Okay, so you have two actions. You have the action of the Hecke algebra on the tensor space, and you have the action of GR and Q on the tensor space too. So this is a very familiar picture. So this is called the q-Schur algebra. Now, when n is bigger than or equal to d, then it turns out the tensor space is actually a projective module for the q-Schur algebra. So you have an item problem which reflects the projectivity. So for n bigger than or equal to p, there exists an item problem inside of S such that E, S, E is going to be an issue. Okay, so you can actually get to the modulus of the Hecke algebra by using this item problem. So nice thing is there are these functors. So there are these functors which are quite important. So you have a functor which maps S modules to H modules. Okay, so all you do is you take an S module and just you hit it by judgment. So F is going to be equal to E. Okay, so the people who are familiar with this is just what's called the Schur functor. This is an exact functor which allows you to sort of classify the irreducible modules for H and irreducible modules for S. So the ones which don't get killed give you a complete set of irreducible modules. Now, what people don't study so much is the adjoint, or AF. So this is the adjoint which goes from H modules to S modules. And this is
I'm a little bit confused. You're taking H endomorphisms of B times 50.
yeah. It's just like you take the symmetric group algebra is symmetric, right? You just get the Schur algebra. So it's just the analog of that. So that's how you go.
So ESE is equal to H, then H commutes with the H action.
Yeah, so S and H, yeah, they commute, they're commuting actions.
But you're saying that H is sitting inside S?
No, well, it is in terms of looking at the image of ESE. Yeah, I mean, it doesn't contain a unit, but it's a common trick with item. You take an algebra
You
that's
as a GLN and the symmetric group. You just have the symmetric group.
The S is the image of J.
That's right. Yeah, I mean, it's built into this picture. All right, so
It's still unnerving because somehow S and H act on opposite sides and commute.
Yeah,
I do, yeah, that's
That's how you're saying, well, there's actually the copy of H inside S.
well, it's,
H is not commutative.
let's talk about this later. Yeah, let me keep on going. Right. So what you have is you have these functors which go from H to S modules, and what you're doing is you're using the double centralizer property here. So you plug in the tensor space. It's a left module for HQ sigma D, and it's a right module for S. So this whole thing becomes a left module for S. So this uses meaning. Okay, so one way to think about this is that you're building in Schur probability functorial. That's what we're trying to do. Now, the nice thing is when you have these functors, so back in the 90s, I was thinking, well, everybody's studying Schur duality at this sort of zero level. So at the Hom level, you can actually encapsulate Schur duality using Homs. But what about higher right-derived functions? And it turns out you can get a spectral sequence which relates to Coulomb. So in the 1990s, which worked out ability so, and we created a spectral sequence which relates these. So E2 ij, and this is going to be equal to, you're looking at X over the Schur algebra. And then you look at the higher right functors, G, and that's going to converge. So this is a very nice spectral sequence, the first order spectral sequence. And it's going to converge to X I plus J. The Hecke algebra. We apply F to us and we apply N. All right, so if we just stare at it for a second, we could see, if you take the higher right derived functors of this, it actually packs a lot of information in about the commuting actions. So in characteristic P, or L is the word of unity, you can get a lot of information by using this spectrum. Okay, so let me give you an idea of how this proof goes over here. All right, so here's the idea. So the idea is to use the functor G. So suppose that M has a spectral friction. Okay, so let's say there's M, and let's say you have a filtration, and I'm just kind of drawing this. So let's say this is at the bottom, and then this kind of goes up. And these are the subjunctions. And then what you do is you tensor M by the sign representation. So we'll just tensor this by the sign representation. And then you get these modules just by the sign. Okay, so you want to keep track in terms of how many times these things appear in the filtration. Okay, so I have to give you some facts. So for L bigger than or equal to 4, it turns out that the higher right derived functors of these sections, S mu tensor sign, is going to be actually equal to 0. Okay, so this is an important fact that you have to use in this term. And then the second fact you're going to need is that you can realize these modules via a co-standard model. So remember, so the fact about the situation is this should actually be a quasi-hereditary algebra. So modulus for S on our highest weight count. So S mod, so S mod is a highest weight variable. All right, so that means that you have co-standard modules and your standard modules, and the filtration multiplicities for those are all. Okay, so now what you do is you just hit the filtration by the G over here. So then you consider G on M. Okay, so because of the higher right, the first right derived functor being 0, everything's going to remain exact. And then what you can say is that the number of times this S mu appears in this filtration is the same thing as the number of times its sign counterpart appears in here, which is equal to the number of times G on M with the co-standard model. Okay. So this has a vial filtration or standard filtration, and because you have quasi-hereditary algebra, it's quantity as well. And that doesn't. And so you can take an arbitrary filtration for your involving Schreck models, and you could say that it's always the equal to this filtration models. So that's all. All right,
When you do those three,
where did what?
where we have characteristic three.
Oh, here, you have to, this is a very important, this actually holds for all the different. All right. Now, why does this work for like symmetric groups? You want to put the side over here. Just a little bit on the side. So, anybody guess why this works for symmetric groups? Why you want the characteristic bigger than 5? So it works basically because the alternating group is simple. For n bigger than 5. So what that does is it forces on this condition. So when you think about it, you really want to know something about extensions between the trivial one and the sign representation. And this is 0 and 4. So it's a simplicity of alternating group. Comes in the money. Okay. Any questions? Okay, so this is kind of how am I going to do this? Okay. All right, let me see if I can maneuver this. So I think I it's the bottom first, but not talk about. So let me do that. Where's it? So erase the bottom right there. Up. Stand slightly sides to each of the cells. If not, okay. All right, I think we're okay. All right, so this I would call sort of prehistoric history. And so it turns out that Rouquier saw this and he developed his theory of one colors sort of based off of this theory. So the next thing I want to talk about is Rouquier's quasi-hereditary one color. So instead of one covers, I'm going to look at I cover. And this was from 2008. So what Raphael did was he actually developed the theory of one covers. And the reason why he wanted to sort of develop the theory of one covers is that the quasi-hereditary algebras here did very well homologically. Now, the Hecke algebras or the group algebras don't behave as well homologically. So that's why he developed this theory to sort of encapsulate what things behave very well. All right, so the let S a say this is a quasi-hereditary algebra, or S mod is a isolated category, and H is just a finite-dimensional algebra. Okay. So SF is a quasi-hereditary high cover. If and only if there exists an exact functor structure going from what's the mod with the H model. Okay, so the way you think about it is a credit line notation. So this is an example of quasi-hereditary property. Such that let me see if I can. Right, for now, let me see if I can smooth this quote down. So such that I have a couple of properties. So one, H is the endomorphism of S of P off, where P is the projective as a module. Two, this script F actually comes from this P, so it's just a Hom function. So this is going to be equal to Hom over S of P prime. And then you have to have certain conditions at the 0th level and also at the higher X level. So one is that Hom S of MM is preserved under a phi F. So it's an F of M, F of M. Okay, and this is for all M projected estimates. Okay, and then 4 xi or xj s of MM. This is also preserved. But you need a condition on M and N. So where M and N have co-standard filtrations. So for every M and N with these delta filtrations, standard filtrations. Okay. And this happens for all j between 0 and up.
Is it on the right side?
Oh, sorry, this is Madison. Good, everyone's paying attention. That's check. Thanks. Okay, good. All right. Let me move this a higher. If one uses this board. And let's see. All right, so let's see how this relates to this example from here. Okay, so let me mention that the largest I for which this is true so this is a name that I didn't invent, or Dave didn't invent. Okay, so this is actually called the Hammer complement dimension. So I'll just say HM dimension. So you'll see this in the literature. Okay. And so what happens in this situation over here? So let's look at this example. So S is SQ and D, and H is the Hecke algebra for type A. And then the projective model here is potential space. Okay, so you just sort of plug everything into Rouquier's definition. So the HN dimension turns out to be equal to (-2). This is computed by somebody. And another thing to sort of think about is how do these properties arise? Well, they rise by, you can use the spectral sequence over here. And you can see that if these higher right parameters vanish in a certain range, then these properties are going to hold. Okay? So the spectral sequence here very much is a part of this game in terms of the Rouquier quasi-hereditary hypothesis. See, and then for
We said largest I, you mean overall possible S and a fixed vector.
yeah,
This is the property of H.
yeah. So this for this condition is for all M and M. So you fix
So, when you say the largest line,
for which 4 is true,
which,
for which property 4 is true.
I see, the fixed S, isn't it?
Yes, yeah.
Okay.
What's up? You okay? Okay. All right, so for L bigger than 4, one has a quasi-hereditary 1 couple. All right, so for the remainder of the talk, I'd like to take this type A picture and see what happens in other types. All right, so now we have to move on in history. Okay. I don't like using this board. Can I just erase this board and use this? Is that right? Oh, okay. Yeah, this one's just too high. All right, so I'll just erase this board and use this. All right. So, okay. All right, so the next thing I want to talk about are rational parenting. All right, so the story goes as follows. So W is a complex inflection group. And Eckendorff and Ginsburg created these things called complex reflection algebras, symplectic reflection algebras. So these are called HWs, and these were developed by Eckendorff and Ginsburg. And they actually use these, and these are called, actually, let me just say they're called rational parenting. Okay, so there's sort of an explicit construction by using the group algebra, the complex reflection. Now we sort of build this up by using this. Okay, there's a parameter too, but for this talk, I'm not going to worry about the parameter. So, all right, now later on, Ginsburg, Way, Opdon, and Rouquier, and this was in 2003. They developed a category O for these symplectic reflection algebras, for these rational programs. So they developed category O for each of them. Right. Now, in doing so, what was their motivation for developing all this? What they wanted to do was they wanted to create quasi-hereditary covers for these, the Hecke algebras corresponding to these complex reflections. So if you read their papers, that was their motivation for doing this. So this whole theory generalizes the theory that I just about the q-Schur algebra. Okay, so this is sort of a vast generalization. And all of this was
H W again?
sorry, HW. Yeah, and so the idea was this is a very geometrically defined category, and the functor is geometrically defined too. And if you read their papers, there's lots of dumb operating. Oh, with the options. All right, so let me state a problem. So again, this is very geometric, and we're algebras, so we want to see things in sort of more down the way. So we call this the GGOR GGOR problem. And so here's the problem. So I want to find a concrete finite dimensional algebra. I don't mean like I'm taking an endomorphism algebra projections. I mean a concrete algebra with a basis, for example, nice basis. Okay. Containing an item problem. Let's call this algebra S. QW. Such that this item code is an SQW. Such that. So remember with W, there's always a Hecke algebra involved. So I want E times S times E to be equal to the Hecke algebra. So the Hecke algebra, HQW is going to be E times SQ. Okay. And then what I want is I want compatibility with this rational problem composition. So two corresponding Schur problem strip that. This makes the problem diagram neat. Okay, so here I have the category O for this rational Cherednik algebra. And I'm going to have some sort of map from the modulus of this to the modulus for SQW mod. And what I want this sort of functor to do is to do some equivalence. And here you have the famous KZ problem. Okay, so this goes from this to HQ mod. F mod. And then we have a functor which goes like this, and this is just the output. Okay, so you want this whole picture to commute, and you want this here to be equal. Okay. So the idea is that you want to find a finite dimensional algebra, a nice one, which actually gives you the category O for the rational Cherednik. That over you want to do.
You need to find the equivalence as well.
You need a.
The equivalence is also, you have to find it.
Yeah, this is a good question because there's a theorem by Rouquier which allows you to actually get this by looking at. So you have this functor down here and this functor down here, and what you do is you show that the ordering on the weights is a refinement. So the ordering here is a refinement of the order. And once you do that, then the equivalence comes. So this is called Rouquier's unicity. So you have a tool to actually do this. We don't have to build it by hand. Okay. So the last part is I want this to be one. SQW mod H mod. This is one. This is very important for this theory. Now, it turns out that Rouquier proved that this is actually one color ring. So basically what you're doing is you're comparing quasi-hereditary one colors and using that theory. So we just can't do this on the level of covers. We have to go up one level with quasi-hereditary one color. Yeah. All right. Okay, so I'm gonna be a little bit more sketchy on how this is done. So this is solutions. The GGOR problem. All right, now to actually build this up, what you need to do is you need to use Rouquier in this group. I'm not gonna state it. So the idea is to use Roukier's. What's called unicity. And so what you do is you construct. You need to construct this shrub. You're going to construct SQW. And then you also want to construct F. And then what you need to do is, this is already given to you. The irreducibles are sort of well understood in terms of how they're parameterized. So what you do is you sort of look at the ordering, which induces ordering on the irreducibles downstairs over here. And then this is given by head code. So you have irreducibles up here, a certain ordering given by a nice weight structure. You push it down here, and then you need to compare the orders. And then the idea is compare the orders. Okay. And so once you have these conditions satisfied, then you have this. So then you have this. Okay, so let's go through some cases. Let me see, I wonder whether I should put this up for. Okay, you want this kind of written down or no boxes. All right. Okay, so there's been work done on this. So Rouquier actually showed that one can do this for type A. So let's look at Weil groups. So for type A, then you can make this SQW to be the q-Schur algebra. I can just make this a P here. Okay. And of course, you need the conditional bigger than or equal to 4. And this was done by Rouquier in this paper. And then 2008. Okay, so the type A condition or situation is completely understood. How about for type B? Well, I can sort of go a little bit outside of type B, and so I'm kind of sad that Yvonne's not here, but so Ian Gordon and Yvonne Losa actually solved this problem for cyclotonic calculations. So they did the following. So let H be, so let me just write it down, right? So this is due to Gordon and Losa. And this is 2011. Okay. So what they did was they looked at H being the cyclotonic Hecke algebra. So this has a certain type. Don't ask me about all this notation, right? You can kind of see where it comes from. So you have to use G, R, 1, U. Okay, so this is associated to the complex reflection group Z, obviously R, 3, sigma 8. Okay, and so they proved that the GGOR problem is solved by using the cyclotonic q-Schur algorithms. All right, now, people have actually worked on cyclotonic Schur algorithms. They're not so easy to piece to actually work with. So they're given by looking at some sort of endomorphism algebra of the Hecke algebra. And you have to take a direct sum of these permutation modules. All right, so this is a nice solution. It's a very nice solution to this problem. But let me show you a more beautiful solution for the GGOR problem. So it's I don't know, Bulgaria, do they have beauty contests?
Not very popular.
Not very popular. Okay, sorry. Anyway, so what I'm going to do is I'm going to show you another solution for this GGOR problem, and you'll see that maybe this solution is a little more than.
Just to be sure, when you say using, you mean that is S, you got it.
That is what?
When you say using this algebra, you mean that is S, you got it.
Yes, that's right.
So is.
All right, let's see. Again, I have some. All right, so this is where we jump in. So this is work that we did. And so let's specialize down to the case where R is equal to 2. So we're looking at the Weil group for type B. So W is symmetric group symmetric by DQ. Okay. So this is the Weil group of type near C. Okay. Now, it turns out that there is an action of the Hecke algebra on the tensor space. So there is an explicit action of the Hecke algebra on the tensor D in this situation. Okay. And the nice thing is that this action is very compatible with the type A action. So I'm going to actually draw the picture of it. Okay, so in the middle, we're going to draw the tensor space. So here is the tensor space over here. Very nice object. Now upstairs, I'm going to do the type A picture. So the type A picture is very, very classical picture. So what you do is you have the Hecke algebra which acts on. So HQ sigma D. Okay, so the top one, you should think of it as type 1. Okay. Now, the Hecke algebra for type B embeds in the Hecke algebra. Actually, the Hecke algebra for type A embeds in the Hecke algebra for type B. Okay. Very natural way. And this action over here is compatible with this. This action. Now you can ask yourself, what is a conjugate? Okay, what things actually can you? And it turns out that when you ask that question, you get the I quantum. So upstairs, you get, let me just write it this way. So this is the quantum maker space. So this is, so again, quantum space, not the blanket. I'm not doing quantum. Okay. So what you do is you take the coordinate algebra of a quantum matrix space, you take its dual, and you take the dehomogeneous component, and it's a well-known fact that this actually realizes the Schur. And this, of course, acts on the tensor space too. And when you take the endomorphism algebra of this is going to also act. So what we call this B and D. And this is the endomorphism algebra. This is also going to act on this. Okay. Now, how do you actually get something like this coordinate realization in type B? Well, what you have to do is you have to factor out by a right ideal. So you take a right ideal out of it, which is actually defined by the relations which are related to the I quantum group. Then you actually can realize this inside of it. Realize the q-Schur algebra with the tensor space in terms of the quantum meter space. And of course, this injects inside of it. And so this comes from the I quantum group. So if you want to look at the enveloping algebra picture, so now we'll just back it up a little bit. So here's the enveloping algebra picture. UQGLN. Okay, so I'm not sure if this is the right notation. I'll just call it BGLN. So this turns out to be an implied sub. So this is like one. This is society. Okay. All right, so the nice thing about this, so what's nice about this compared to the cyclotomic q-Schur algebra situation is that the tensor space comes into play over here in a very, very natural way. And if you just glue together permutation modules, you don't see that quantum group at all. That's missing. But when you actually use the full tensor space, then you get a much more beautiful picture, which is compatible with the classical type A picture upstairs. So there's the type A picture over here, and so the type B C picture. Okay. So in some ways, the more optimal GGOR solution is when you can actually realize is q-Schur algebra in terms of the endomorphism algebra in tensor space. And in most cases, the models for this algebra are more equivalent to the models for the cyclotomic q-Schur algebra under certain conditions. There was a fair amount was approved by one of them students. Okay. Don't have too much time.
They just clarify, so V has dimension n for any n.
Yeah, it does.
And
It does, because of this. It's a natural representation. GR.
there's other Hecke algebra, so if Q is 0, Q is 1, sorry.
Here's one you get the spectral group situation.
The extra reflections is act by -1 on each factor
Yeah.
or something, some obvious thing.
That's right.
So V has nothing to do with any fundamental representation. That's the B.
Well, I mean, it's a representation for this sort of ambient group. And you could just do it, you could sort of do this sort of more abstractly. Well, let me not get into this. Right. Okay, so I won't have too much time to say things about type D. So we actually solved this for type D. Okay. All right, so let me just say a few things about type E. All right, so it turns out the Hecke algebra, there's a great equivalence between the even type T situation, and this is great equivalence, between an algebra called AM, and then you have a bunch of type A stuff, which we know how to handle. So this algebra is what we call the Q algebra. And this is an algebra which is an example of a quantum Reed product that Sasha bought about. So AM is a quantum Reed product. And in Sasha's talk, he talked about how you can make quantum Reed products act on tensor spaces. So this is going to act on tensor space, the tensor 2. Okay. So we have an action of AM on this. We have an action of all the type A stuff on tensor space also. Okay. So the right-hand side, we can actually put an action on tensor space. Okay. We actually don't know how to put an action on this Hecke algebra on tensor space. That's still conjecture. But we can still use the actions over here, the rate equivalence. And we can actually construct the Q-Schur algebra by using the endomorphism algebra, this stuff on tensor space.
Actually.
And I will talk. Oh, I thought I had one there. Okay. All right. So then what you have is you have a Q-Schur. That's to okay. And we'll call this S. What we spell S and 2. Okay, so this is the Q-Schur algebra that you get from this situation, and this actually solves the GGOR. Okay, so let me just mention one more thing. So the question we have is, when you take any file group, and you actually find some sort of action of the Hecke algebra of the file group on a tensor space, which actually gives this picture of complete. So we don't want to just glue together permutation modules. We just say, well, games up. But we actually want to have a concrete realization that you can work with and face these and neighborhoods, which actually is very important to the rational Cherednik situation. Okay, we stop it.
Any questions? Time for one question? Yes?
Can you realize this algebra is a centralizer or something on some module? Like the other two?
So what we do is we sort of do it artificially here. Is that you just use this die,
Mm-hmm.
and then we hit the endomorphism algebra on the tensor space.
Mm-hmm.
That's all we do.
Mm-hmm.
And then we show that it works.
Mm-hmm.
We have to use a lot of the things that I didn't mention in the hammer and Nakano stuff.
Mm-hmm.
The inverse one.
More question, I guess. Do you have a question? Saw your hand raised.
No, well, I can ask you a question.
Yeah.
Can you tell us what the I-quantum, which I-quantum this is?
Yeah, it's, I think the one where you just, I mean,
You have one dot.
yeah, and then you say,
Do you use the other ones as, can you use the other ones as well of type A?
that's a good question. I don't know the answer. But there's a natural one which comes up in this picture. You can look at it. It's all laid out in our papers.
Sure.
All right, let's thank Dan again.